Example 1. Test whether the following sequences are geometric progressions, GPs. Now a sequence is a GP if Tn plus 1 over Tn is equal to Tn over Tn minus 1, where Tn minus 1, Tn and Tn plus 1 are 3 consecutive terms of the sequence. Now another way to test if a sequence is a GP is if we take, say, 3 consecutive terms and we square the middle term and we multiply the 2 terms on either side of the middle term and we find that they are equal, then that's also a geometric progression. So let's have a look at part A. We have this sequence here, 5, 15, 45, 135 and so on. Now by observation we can see that if we take the first term, multiply it by 3, we get 15. We take 15, multiply it by 3, we get 45. 45 multiplied by 3, we get 135 and so on. But just applying the test, so if we choose, for example, 3 consecutive terms, say 15, 45 and 135, and we divide 135 by 45, so that's the Tn plus 1 divided by Tn, and then compare that with Tn divided by Tn minus 1, and we get the same value, the same ratio, then we can conclude that the sequence is geometric. So 135 over 45 equals 3. 45 over 15 also equals 3. So therefore the sequence is geometric with the first term being 5, so A equals 5, and the common ratio is 3. Let's have a look at part B. 5, 10, 15, 20. Now this we know is an arithmetic progression. So if we take any term and we just add 5 to it, we get the next term. So clearly this is not geometric, but let's prove the point. And we're going to use this rule here. This is the Tn plus 1 times Tn minus 1 is equal to Tn squared, and compare and check to see they are the same. So again, choose 3 consecutive terms. So for example, I'll choose 10, 15 and 20. 10 multiplied by 20 is 200, so that's the Tn plus 1 multiplied by Tn minus 1. And then let's square the term in the middle, so this 15, so if we square that, 15 squared is equal to 225. They're clearly not the same, so therefore the sequence is not geometric. So either definition is fine. Let's have a look at one more example. So if we have a look at part C, so we have pi, pi cubed, pi to the power of 5, pi to the power of 7, and so on. Again, let's just choose any 3 consecutive terms. You can choose 4 consecutive terms if you like as well. So just for prudence, if you want to just make sure 100% or at least as much as possible that this is a GP, you can test as many terms as you like, but the minimum number of terms is 3. Again, I'm going to choose pi cubed, pi to the power of 5, pi to the power of 7. Pi to the power of 7 divided by pi to the power of 5 is pi squared. And pi to the power of 5 divided by pi cubed is, again, pi squared, so there's our common ratio. So therefore the sequence is geometric with the first term A equals pi and the common ratio R equals pi squared. So just as another side note, if we have 3 terms, let's say A, B, C, and they form a geometric progression, then B squared is equal to AC, and we've seen that already with this test here. So imagine that's B squared and that's A and C. Okay. So if A, B and C form a GP, then B squared is equal to A times C. And if we take the square root of both sides, B is equal to plus or minus the square root of AC. This is actually known as the geometric mean. So just as a little side note there. Example 2. Write out the first few terms of the GP with A equals 4 and R equals 3 and determine the value of the 13th term. So we can use the non-recursive formula for the general term of a geometric progression. That is, the nth term, Tn, is equal to the first term A multiplied by R to the power of n minus 1, R being the common ratio. And we need n minus 1 common ratios because we start off with the first term, but to get to the second term, we just multiply by 1 lot of R. To get to the third term, we multiply by 2 lots of R, so R times R and so on. Hence why it's n minus 1. So in this example, A is equal to 4, common ratio is equal to 3. So Tn, the nth term of this particular GP, is equal to 4 times R to the power of n minus 1, of course with n equals 1, 2, 3, and so on. So the first few terms of this GP, starting off with 4, multiply that by 3, we get 12, multiply that by 3 again, we get 36, multiply that by 3 again, we get 108, and so on. Now to get the 13th term, we can just apply the formula directly. So T13, so that's the 13th term, is equal to 4 times 3 to the power of 12, so it's n minus 1, 13 minus 1, and that equals 2,125,764. Example 3. Find a non-recursive formula for the GP given by the recursive formula Tn equals Tn minus 1 multiplied by negative 2, where T1 is equal to 3. Now firstly, let's write out the first few terms of the GP just so we can see a pattern. Now, T1 equals 3 refers to the first term, A. So starting off with 3, to get to the next term, we multiply by negative 2, so 3 times negative 2 equals negative 6, negative 6 multiplied by negative 2 is positive 12, positive 12 multiplied by negative 2 is negative 24, and negative 24 multiplied by negative 2 is positive 48. So notice that you get like an alternating pattern here, positive, negative, throughout this GP. And that's a hallmark of any GP that has a negative ratio, in fact. Next, let's find the common ratio. Now, we don't need to prove that this is a GP. In fact, we're told this in the question, so no need to spend sort of extra time on that. So all we need to do is just pick any two consecutive terms. So I've just chosen T3 and T2. So to find the common ratio, I just take T3 divided by T2. So there's T3 divided by T2, 12 over negative 6, and that gives us a common ratio of negative 2. So again, any two consecutive terms will be fine and will give you an R value of negative 2. Finally, we can find the non-recursive formula for Tn. And of course, Tn is given by the formula A times R to the power of n minus 1. And we've determined the first term and the common ratio. So A equals 3 and R equals negative 2. Therefore, Tn is equal to 3 times negative 2 to the power of n minus 1. Or if you want to simplify that further and just express it just in terms of n rather than a power of n minus 1, in fact, we could write it as Tn equals negative 3 over 2 multiplied by negative 2 all to the power of n. So either one of those two formulas will suffice. Example 4. Determine whether 320 and 720 are terms of the GP, 5, 10, 20, and so on. Now to help us with this problem, we will use the formula for the nth term of a GP, that is Tn is equal to AR to the power of n minus 1, where A represents the first term and R represents the common ratio. Now, if Tn is a part of that GP or part of that sequence, then there will be a positive integer value of n such that AR to the power of n minus 1 will give us that Tn. So we're using this formula in reverse and just solving for n each time. And what we're looking for here is a value of n that is a positive integer that corresponds to the position of the particular value in that sequence. So it doesn't make sense to have a decimal value for n, since position or rank is a whole number. So firstly, let's test Tn equals 320. So we're going to solve this equation for n and see or check that n is in fact a positive integer. Hopefully it is. 5 times 2 to the power of n minus 1 is equal to 320. Dividing both sides by 5, we have 2 to the power of n minus 1 equals 64. And we can see by inspection that 64 can be expressed as a power of base 2. So 64 is equal to 2 to the power of 6. And just re-expressing this equation here as 2 to the power of n minus 1 equals 2 to the power of 6, and then equating the indices, we can see that n minus 1 equals 6, therefore n equals 7. That's a positive integer. In fact, that corresponds to the 7th term of the GP. So 320 is the 7th term of this particular GP. Let's have a look at 720. I'm going to test Tn equals 720 in the same way. So 5 times 2 to the power of n minus 1 is equal to 720. Dividing both sides by 5, we have 2 to the power of n minus 1 is equal to 144. Now at this point, without using logarithms, we can see by inspection that there's no integer power of n or integer power of base 2 that'll give us 144. In fact, the closest one will be 128, and it goes to 256 and so on. However, just for completeness, let's use logarithms here to find the value of n and then show that that value of n is not an integer, nor is it a positive integer for that matter. So taking the natural log of both sides, so ln of 2 to the power of n minus 1 is equal to ln of 144. Applying log law number 3, so we can take the n minus 1 out to the front. So this becomes n minus 1 in brackets multiplied by ln of 2 is equal to ln of 144. Dividing both sides by ln of 2 and then adding 1 to both sides, we have n equals 8.1699 and so on, which is not an integer. Not a positive integer, but it's not an integer altogether. So therefore, 720 is not part of the geometric progression. Example 5. The third term of a geometric progression is 12 and the seventh term is 972. Write out the first few terms of the geometric progression. Now we'll use the formula for the nth term of a GP, Tn equals a times r to the power of n minus 1. And we have two known values or two known terms in the sequence. So we have the third term, T3 is equal to 12, and we have T7, the seventh term, is equal to 972. So the strategy here is to form two equations using this formula and then solve it simultaneously for A and R. So using T3 equals 12, 12 is equal to a r to the power of n minus 1, so n minus 1 in this case will equal 2, and our second equation will be 972 is equal to a r to the power of 6, so 7 minus 1 gives us 6 there, and then dividing 2 by 1, so equation number 2 by equation number 1, we can then solve for r, then we can solve for a. So 972 divided by 12 is equal to ar to the power of 6 divided by ar squared. Now the a's cancel. We have r to the power of 6 divided by r squared is equal to 972 over 12. 81 is equal to r to the power of 4. Now because the power of r, the index of r is an even number, we're going to have a positive and a negative value for r, or they're the two possibilities. So r is equal to plus or minus the fourth root of 81. That's the square root of the square root of 81. And we need to consider both cases. So hence r equals negative 3 or positive 3. Now either one of those two values for r, if you use say equation number 1 to determine the value of a, we have 12 equals a multiplied by well, plus or minus 3. It doesn't really matter. You're going to square it. It's going to become either 0 or positive anyway. And we end up with a equals 1 1/3. So to write out the first few terms of this GP, we have a is equal to 1 1/3, and the common ratio r is either positive 3 or negative 3. And we need to consider both cases because we're not given any other information in the question. We might be told, or could be told, that r is positive or r is negative. In that case, just state the particular sequence based on that value of r. But since we're not told, we need to state both possibilities as they are both valid solutions. So case 1, r is equal to negative 3. The GP is 1 1/3, negative 4. So just multiplying everything by negative 3 or the previous term by negative 3 to get the next term along. So 1 1/3, negative 4, positive 12, negative 36, positive 108, and so on. So you can see that alternating pattern there with the plus or minus terms. Now case 2, r is equal to positive 3. And since we're starting with a positive first term or positive a, all the terms will be positive. So it's very much like case 1, just all terms positive. So the GP is 1 1/3, 4, 12, 36, 108, and so on.